Every large-scale system you use today, Instagram, Discord, YouTube, started with a single database on a single machine. That is not a bad decision, it is the right decision at the start. But at some point, that one machine stops being enough. In this video, we are going to trace exactly how engineers solve that problem, layer by layer. We start here in part 1 with the question, what actually breaks first and why? Picture a straightforward setup. Your application, one Postgres instance, one server. Day 1, it handles everything fine. Now imagine 10 million users. Let's look at what starts cracking. The first limit you hit is connections. Postgres's default max connections is 100. Each connection is a separate OS process, consuming roughly 5 to 10 megabytes of RAM. Even with a connection pooler like PG Bouncer in front, you have only moved the bottleneck. The database engine itself can only process so many queries in parallel. One well-tuned server handles roughly 10,000 to 50,000 simple queries per second. The moment your query mix involves joins, aggregations, or full table scans, that ceiling drops dramatically. But raw throughput is only part of the story. The deeper problem is latency, and it has a cliff. When your hot data fits in the database's buffer pool, reads go straight to RAM. RAM access time is around 100 nanoseconds. The moment your working set grows larger than what fits in memory, the database must reach for storage. An NVMe SSD read takes around 100 microseconds. A traditional hard disk seek takes around 10 milliseconds. That is a difference of 100,000 times between RAM and spinning disk. Once your working set exceeds the buffer pool, latency does not increase gradually, it falls off a cliff. The first instinct when things slow down is to buy a bigger machine. Vertical scaling is real and it does work. For a while. Amazon Web Services offers instances like the U24TB1.metal. 24 terabytes of RAM and 448 virtual CPUs. That is genuinely enormous. But cost grows superlinearly as you climb those SKUs. And there is a hard ceiling. AWS offers a finite set of instance types, and you will eventually reach the largest one. More fundamentally, a bigger machine solves throughput, but it does not solve the next problem. One machine is one failure domain. If the hardware fails, a power supply fails, a kernel panics, your entire product goes down. Every user, every request, gone until you recover. There is a third structural problem, separate from capacity and availability. All writes serialize through one write-ahead log on one disk. The WAL is how Postgres and MySQL guarantee durability. Every write is flushed to the log before it is acknowledged. That log lives on one disk on one machine. No matter how many CPUs you add, all your write traffic must pass through that single sequential bottleneck. So to summarize where we stand, one database means a connection limit, a throughput ceiling, a latency cliff once data outgrows RAM, a vertical scaling wall with superlinear cost, a single failure domain, and a single writer bottleneck on the WAL. These are not theoretical concerns. They are the exact sequence of pain that real engineering teams hit as their products grow. The rest of this video is about the techniques engineers have built to break through each of these ceilings one by one. We will look at read replicas, caching layers, storage engine design, sharding, consistency trade-offs, distributed consensus, and finally, a reference architecture that puts it all together. Let's get into it. Read replicas are the first move almost every team makes when a single database stops keeping up. The idea is elegantly simple. Keep one node as the primary and let it stream every change to one or more replicas. All writes go to the primary. The replicas just follow along. Reads, on the other hand, can go to any replica. Add more replicas and your read capacity scales nearly linearly with each one you add. This is called primary replica replication, and it is the backbone of virtually every large relational database deployment in production today. Under the hood, the primary writes every change to a log. Postgres calls it the write-ahead log. MySQL calls it the bin log. Each replica tails that log and applies the same operations in order, staying in step with the primary. So how does the data actually travel? Most systems default to asynchronous replication. In async mode, the primary acknowledges a write to the client the moment it commits locally. It does not wait for any replica to confirm. The replica will catch up shortly after, usually within milliseconds. But under heavy load, that lag can stretch to seconds. And if the primary crashes before shipping those changes, they are simply gone. The replica never saw them. This is called RPO greater than 0. Your recovery point objective admits some data loss. Synchronous replication closes that gap. Here, the primary holds the write until at least one replica confirms it has been applied. No data loss on failover, but now your write latency equals the primary's commit time, plus the round trip to the slowest sync replica. Worse, if that sync replica goes offline, the primary can block all writes while it waits. The practical compromise most teams land on is semi-synchronous replication. One replica is synchronous. That is your durability guarantee. The rest are asynchronous. That is your read throughput. You get the best of both, one acknowledged copy for safety and many lagging copies for read scaling. Now here is where replication gets genuinely tricky. Replication lag creates anomalies that feel like bugs to your users, even when the system is working exactly as designed. The first anomaly is called read your own writes. Picture this. A user updates their profile photo, the write commits on the primary, and then their next page load is routed to a replica that has not caught up yet. Their new photo is gone. They see the old one. From their perspective, the app just ate their change. The fix is to pin that user's reads to the primary for a short window after any write, say a few seconds. A cleaner alternative is to track the log sequence number of the write and only route a read to a replica that has at least caught up to that position. The second anomaly is monotonic reads, or rather, the violation of it. If consecutive requests from the same user land on different replicas, they might see data from different points in time. A feed item that appeared 2 seconds ago might vanish on the next refresh, because that request hit a lagging replica. Time appears to go backward. The fix is to stick a given user to the same replica for the duration of a session, so at least their view is self-consistent. Both of these anomalies are a preview of a deeper truth. Distributed systems make you choose which guarantees you actually need, and they do not give you all of them for free. Beyond lag anomalies, failover itself is hard. When a primary dies, something must detect the failure, choose a replica to promote, and repoint every client to the new primary. The detection step is tricky. Is the primary dead, or is it just slow? Or is there a network partition? Timeouts lie, and if the old primary comes back while the new one is already accepting writes, you have two nodes that both believe they are the primary. That is split brain, and it can corrupt your data. This is exactly why serious systems use consensus protocols, Raft or PACELC, to make promotions safe, and we will get to that in a later part. One real-world data point: Instagram ran sharded Postgres with replicas for years as its core read scaling strategy, while growing past tens of millions of users. Virtually every company you have heard of with a large relational database runs at least one read replica. They are not optional at scale. They are table stakes. So, replicas expand your read capacity and give you a hot standby for durability. But notice what they do not solve. All writes still funnel through one primary. The replica count can be 10 or 100, and the write throughput ceiling stays exactly where it was. One machine, one write-ahead log, one disk. In the next part, we tackle the read side from a completely different angle. A cache layer that can absorb the overwhelming majority of your reads before they ever touch the database at all. In the last part, we saw how primary replica replication lets you fan out reads across multiple machines. But replication lag reminded us that distributed systems always come with trade-offs. Now there is a faster trick that sits in front of your database entirely: a cache. A cache stores the results of expensive lookups in memory, so the database never has to answer the same question twice. The most common pattern is called cache aside or lazy loading. Here is how it works. Your application checks Redis or Memcached first. If the value is there, that is a cache hit, you return it immediately without touching the database at all. If it is not there, a cache miss, you read from the database, write the result into the cache with a TTL, and return it to the caller. The next request for the same key finds it in cache and never reaches the database. There are two other patterns worth knowing. Write-through writes to the cache and the database at the same time, keeping them in sync, but every write pays the cost of both. Write-back writes to the cache first and flushes to the database asynchronously. Very fast, but if the cache node dies before the flush, you lose data. Cache aside is the default in most real systems because it is simple and only caches data that is actually requested. Now, let us talk about the math, because the numbers here are striking. Suppose your cache has a 99% hit rate. That means your database only sees 1% of total traffic. Now drop the hit rate to 95%. Your database load quintuples, 5 times as much traffic from a 4 percentage point drop. Hit rate is one of the highest leverage metrics in your entire stack. A small regression in cache effectiveness can be catastrophic at scale. How much scale are we talking about? Facebook's Memcached deployment, documented in the NSDI 2013 paper, handled over 1 billion cache requests per second across their clusters. A single page load on Facebook could trigger hundreds of individual cache lookups. They stored trillions of items in cache at any given moment. A single Redis instance can serve around 100,000 operations per second. Redis cluster scales that horizontally. Add more nodes, push into the millions of ops per second. Now, about cache invalidation. Phil Carlton famously said, "There are only 2 hard things in computer science: cache invalidation and naming things." The joke lands because it is true. When the underlying data changes, how does the cache know? The simplest strategy is a TTL, time to live. The cached value expires after n seconds, and the next miss fetches fresh data. Explicit delete on write is cleaner. When a write happens, you delete the cache key immediately. Version keys are another approach. Embed a version number or timestamp in the key, so stale entries are simply never requested again. Each strategy has its own failure mode, and in practice, you often combine all 3. The nastiest failure mode is the thundering herd, also called a cache stampede. Here is the scenario. A hotkey expires. At that exact moment, thousands of concurrent requests all see a cache miss. Every single one of them goes straight to the database at the same time. The database, which was handling almost no load a moment ago, suddenly takes a full spike. One of the most effective mitigations is request coalescing, sometimes called single flight. When multiple requests miss on the same key simultaneously, only one of them is allowed to fetch from the database. The rest wait for that result. Another technique is probabilistic early expiration. Instead of expiring at a hard deadline, you recompute the value slightly early with a probability that increases as the TTL approaches zero. The Facebook paper introduced Memcached leases, which solve two problems at once. A lease is a token issued to the first client that misses a key. Only the holder of the lease may write back to that cache slot. This prevents thundering herds and also eliminates stale set races, where a slow read returns an outdated value and overwrites a newer one. Facebook also built a system called McSqueal. McSqueal daemons tail MySQL bin logs and proactively invalidate cache entries across regions the moment a write is committed to the database. That is how you keep a cache consistent at billion requests per second scale with a geographically distributed deployment. So the cache layer is deceptively powerful. It absorbs the overwhelming majority of your read traffic. It keeps your database from melting under load. And when tuned well, it makes your system feel nearly instantaneous to users. But tuning it well requires understanding hit rate math, invalidation strategies, and the thundering herd problem, none of which are obvious until they bite you in production. Next, we go one level deeper. Beneath Redis, beneath Postgres, beneath every database is a storage engine. And the choice of B-tree versus LSM-Tree shapes everything from write throughput to tail latency. Replicas and caches address the read side of scaling. But there is a layer underneath every database that we have not opened yet, the storage engine. Every database is built on top of one. The storage engine is the piece of software that decides how data actually lands on disk and how it gets read back. There are two dominant designs with very different trade-offs depending on whether your workload is read-heavy or write-heavy. The first is the B-tree, and it is what powers the databases you already know well, Postgres and MySQL's InnoDB. A B-tree organizes data in a balanced tree of fixed-size pages, typically 4 or 16 kilobytes each. When you look something up, the engine walks down the tree. Each level narrows the search until it reaches the leaf page holding your row. That is O of log n time, and it is excellent for range scans because leaf pages are linked in sorted order. Writes, though, are a different story. Every write updates a page in place on disk, and that means random I/O. If the page is not already in the buffer pool, the engine fetches it from disk, modifies it, and writes it back. When a page fills up completely, it splits into 2 pages, which can cascade up the tree. All of this means B-trees are well suited for read-heavy workloads, but random writes are their weak spot. Now enter the LSM-Tree, log-structured merge tree. This design is used by Cassandra, RocksDB, LevelDB, ScyllaDB, and HBase, among others. The core idea is simple. Never do a random write. When a write comes in, it goes to 2 places: an append-only sequential log on disk, the wall, and an in-memory sorted structure called the mem table. The wall is just for crash recovery. The mem table is where the live data lives. When the mem table fills up, it gets flushed to disk as an immutable sorted file called an SS table. SS tables are written sequentially from top to bottom. That is the key insight. No random I/O, no page splits, just one clean sequential write. Over time, you accumulate many SS tables on disk. A background process called compaction periodically merges them together. It reads several SS tables, merges the sorted entries, writes a new SS table, and discards the old ones. Why does this matter so much? Sequential writes are dramatically faster than random I/O at every layer of the hardware stack. A modern NVMe SSD can sustain around 1 million random read IOPS, but sequential throughput is higher still. And more importantly, it does not wear the flash as unevenly. LSM essentially converts a random write workload into a sequential one, which is exactly what write-heavy systems need. But LSM is not free. It comes with its own costs. The first cost is read amplification. To answer a read, the engine must check the mem table, then potentially look through several levels of SS tables from newest to oldest. The mitigation is the Bloom filter. Each SS table carries a Bloom filter, a compact probabilistic structure that can tell you this key is definitely not in this file with high confidence. With around 10 bits per key, you get roughly a 1% false positive rate. That means most SS table files can be skipped without even opening them, so reads stay fast even as files pile up. The second cost is write amplification. A single logical write, say one row update, can be physically rewritten 10 to 30 times over its lifetime as it moves through compaction cycles. That is CPU time, I/O bandwidth, and flash endurance being spent behind the scenes just to keep the LSM tidy. The third cost is that compaction competes for the same I/O bandwidth as your real traffic. When a compaction wave hits, it can spike your read and write latencies simultaneously. This is exactly what Discord ran into with Cassandra, compaction causing tail latency spikes. And it is a problem we will come back to in part 6. So how do you choose? B-tree if your workload is read-heavy and your writes are moderate. The in-place update model means each key lives in exactly one place, making reads simple and predictable. LSM if your workload is write-heavy and you can tolerate compaction overhead. You get much higher sustained write throughput. One more thing worth knowing. The LSM design has spread far beyond its origin story. RocksDB started as Facebook's fork of LevelDB, tuned for high concurrency SSD workloads. Today, it is embedded inside CockroachDB's storage layer, TiKV, the storage engine beneath TiDB, Kafka Stream's state stores, and MyRocks, which is Facebook's MySQL storage engine variant. LSM is everywhere underneath modern systems, often invisible, but always shaping the latency profile you see. Next up, we tackle the write scaling problem that caching and replicas cannot solve. When even a single primary is not enough, use Shard. In the last part, we looked at the engine underneath your database, how B-trees and LSM-trees handle reads and writes on a single machine. But that is the ceiling no storage engine can break through on its own. All your writes still go to one primary node. Replication and caching help enormously with reads, but every insert, update, and delete still serializes through one write-ahead log on one disk. That is the problem sharding is designed to solve. Sharding splits your dataset across multiple independent nodes, and each node owns its own slice, its own key range, or its own hash bucket. Every node is a full primary for its slice, so you are scaling write capacity in parallel. Let's start with the simplest approach, range sharding. In range sharding, you carve your key space into contiguous ranges and assign each range to a shard. HBase, Spanner, and CockroachDB all use this strategy. Range sharding is excellent for range scans. If you want records between two timestamps, one shard has them all. But there is a classic trap. If your keys are monotonically increasing, auto-increment IDs or timestamps, every new write lands on the last shard. That shard becomes a hotspot while the others sit idle. The simple fix for skewed access is hash sharding. You compute hash of key mod n, and that gives you the shard number. The distribution is now even, no hot tail. But mod n has its own trap. Add one more shard, now n becomes n plus 1, and almost every key maps to a different shard. You have to move nearly your entire dataset to rebalance. This is the problem consistent hashing was invented to solve. In 1997, Kaga and colleagues described consistent hashing, and Amazon Dynamo made it famous. The idea is elegant. Map both your keys and your nodes onto a virtual ring using the same hash function. A key is owned by the nearest node clockwise on the ring. When you add a node, it only takes over the keys that fall between it and its predecessor. When you remove a node, those keys transfer to the successor. In either case, only roughly 1 in n of all keys moves. Everything else stays put. Dynamo and Cassandra both use this ring model. Cassandra refines it further with virtual nodes, or vNodes. Instead of placing each physical machine at one point on the ring, Cassandra historically assigned each node 256 virtual positions scattered around the ring. This smooths the distribution when your hardware is heterogeneous, and it makes adding or removing a node a gradual, balanced operation. Even with perfect distribution, sharding introduces a new problem, the hotspot, sometimes called the celebrity problem. Imagine a celebrity posts something and millions of requests suddenly hit the key for that user's profile. A single shard's throughput limit does not care about consistent hashing. It still gets overwhelmed. Common mitigations include appending a small random suffix to the key to spread reads across multiple shards, aggressively caching the hot entity in Redis, or giving it a dedicated fast path. Sharding also changes what queries cost. A query that touches a single shard is cheap and fast. A query that crosses shards becomes scatter-gather. You fan out the query to every relevant shard, collect the results, and merge them in your application layer. And distributed transactions, where you need to atomically update rows on 2 different shards, lose the single node ACID guarantees you relied on. We'll come back to that in Part 7 when we talk about consensus protocols. Let's look at how Instagram solved this in 2012. Instagram needed unique IDs that were time-sortable, generated at high throughput, and required no central ID service that could become a bottleneck or single point of failure. Their solution was a 64-bit integer with 3 fields packed together. The first 41 bits encode a millisecond timestamp. The next 13 bits encode the shard ID, choosing from several thousand logical shards each mapped to a Postgres schema. The final 10 bits are a per-shard sequence number, giving up to 1024 IDs per millisecond per shard. This scheme was implemented as a stored procedure inside Postgres itself, no extra service needed. The IDs sort chronologically, which makes range queries natural, and they scaled Instagram past 30 million users with an engineering team of roughly a dozen people. Now let us talk about Vitess. YouTube built Vitess to transparently shard MySQL as their write load outgrew a single server. Vitess sits in front of your MySQL nodes and handles connection pooling, query rewriting, and routing. Your application believes it is talking to one database. When a shard fills up, Vitess can split it automatically. Vitess is now a CNCF graduated project, and it powers Slack's entire MySQL fleet and is the engine behind PlanetScale. Discord took a different path when they outgrew MySQL in 2017. At billions of messages, they moved to Cassandra specifically because consistent hashing meant adding nodes without resharding the whole dataset. Only a fraction of keys move when you expand the ring. Sharding is powerful, but it is not free. You are trading a simple, single-node ACID database for a distributed system that demands more from your applications layer and your operations team. The rule in distributed systems engineering is add sharding when you are forced to, not a moment before. In the next part, we step back from the mechanics and ask the deeper question. When your data lives on multiple nodes, what does correct even mean? That takes us to the CAP theorem, quorums, and eventual consistency. Sharding gives you parallel write capacity across many nodes. But now a new question surfaces. What happens when those nodes disagree? That brings us to one of the most important ideas in distributed systems, the CAP theorem. CAP was first proposed by Eric Brewer in 2000 and formally proved by Gilbert and Lynch in 2002. The theorem says, during a network partition, a distributed system must choose between consistency and availability. Consistency here means linearizability. Every read sees the most recent write, as if the whole system were one machine. Availability means every request gets a response, even if some nodes are unreachable. Here is the critical nuance that most explanations get wrong. You do not casually pick 2 of 3. Partitions will happen. Network cables fail, packets drop, data centers lose connectivity. So the real choice is always, during a partition, do you stay consistent or do you stay available? That is C versus A during P, not an abstract menu of 3 features. Now, CAP only talks about what happens during a partition. It says nothing about what your system does the rest of the time, when everything is running normally. That gap is exactly what PACELC fills. PACELC was introduced by Daniel Abadi as a cleaner framing. It says, if there is a partition, choose between availability and consistency, and else, during normal operation, choose between latency and consistency. Under PACELC, DynamoDB is labeled PA/L. It favors availability during partitions and low latency during normal operation. Google Spanner is PC/EC. It keeps consistency in both cases, at the cost of higher latency. This is a much more honest way to reason about real systems, because most of the time there is no partition, and your trade-off is latency versus consistency, not availability versus consistency. So how do systems like Cassandra and Dynamo actually implement these trade-offs at the data level? The answer is quorums. You have n replicas of every piece of data. A write succeeds when W replicas acknowledge it. A read succeeds when R replicas respond. The key insight is this: R plus W greater than N. When that inequality holds, the read set and the write set must overlap by at least one replica. That overlapping replica holds the latest write, so you are guaranteed to read it. The classic Cassandra and Dynamo configuration is N equals 3, R equals 2, W equals 2. With N equals 3, you can tolerate one node being down and still satisfy both R and W. If you set W equals 1, writes are blazing fast, but you risk losing data if that one node fails before the write propagates. If you set R equals 1 and W equals N, reads are instant, but writes become slow and fragile. Tuning R and W is literally turning a dial between latency and consistency. Cassandra exposes this dial directly. You can specify 1, quorum, or all per request. DynamoDB offers eventually consistent reads and strongly consistent reads, where strong reads cost twice the read capacity units. Now, when R plus W is less than or equal to N, you are in the world of eventual consistency. Replicas will converge to the same value, but only after writes stop propagating. This sounds risky, but it is perfectly acceptable for a huge class of workloads: shopping carts, social media feeds, analytics dashboards, user settings. The Amazon Dynamo paper, published at SOSP 2007, is the blueprint for how to build an eventually consistent system properly. It combines consistent hashing with sloppy quorums and hinted handoff. Sloppy quorum means if a target replica is temporarily down, a nearby healthy node accepts the write and holds it as a hint. When the target node recovers, that hint is delivered. This is hinted handoff. For detecting and repairing divergence between replicas, Dynamo uses Merkle trees. Each replica builds a hash tree over its key ranges. Replicas compare tree roots to quickly find which subtree has diverged, then sync only the differing keys. This anti-entropy process runs continuously in the background. Vector clocks handle conflicting writes. Each version of a value carries a clock that tracks which node wrote it and when, so the system can tell whether two writes are causally related or genuinely concurrent. The Dynamo paper directly inspired Cassandra, REAC, Voldemort, and the design of the modern DynamoDB service. Let us close with a real-world reminder of why all these trade-offs matter in practice. Discord ran Cassandra for years to store billions, eventually trillions of messages. Cassandra is eventually consistent and uses an LSM-Tree storage engine with background compaction. During compaction, the JVM would stall due to garbage collection pauses, causing P99 read latencies to spike up to 40 to 125 milliseconds on hot partitions. That is eventual consistency interacting with compaction I/O at scale. Your consistency model and your storage engine are not independent choices. Discord eventually migrated to ScyllaDB, a C++ re-implementation of Cassandra that avoids JVM-GC pauses entirely. We will revisit that migration in detail in the final part. CAP and PACELC are not just academic frameworks. They determine what your users experience when a node goes down, when a network hiccups, or when a hot partition gets hammered with reads. Choose your consistency level deliberately, and make sure your whole stack, from storage engine to replication, supports that choice. Next up, we go deeper into the strong consistency end of the spectrum. Distributed consensus algorithms like Raft, and how Google Spanner achieves globally linearizable SQL transactions using GPS clocks. In the last part, we saw how Quorums and tunable consistency let you trade safety for speed. But there's a deeper problem lurking whenever you need a transaction that spans multiple nodes. Let us start with the classic solution: two-phase commit or 2PC. In 2PC, a coordinator sends a prepare message to every participant. Each participant locks the rows it needs and replies either "Yes, I'm ready" or "No." If everyone says yes, the coordinator sends commit and the transaction lands. Here's the catch. If the coordinator crashes after sending prepare but before sending commit, every participant sits holding locks, indefinitely. They cannot safely commit on their own, and they cannot safely abort. The whole system is blocked until the coordinator recovers. That single point of failure is why 2PC is called a blocking protocol, and why engineers wanted something better. The answer is consensus. Consensus algorithms, most famously Paxos, published by Leslie Lamport in 1998, and Raft, introduced at USENIX ATC 2014, let a cluster of nodes agree on a sequence of log entries without a single coordinator. The core insight is majority voting. A proposal is accepted only when more than half the nodes agree. With 2F plus 1 nodes, you can tolerate F failures and still make progress. And, critically, you can never have two conflicting majorities at the same time. No split brain. Raft was designed to be easier to understand than Paxos while offering identical guarantees. It works in two phases. One node wins a leader election, and from then on, all writes flow through that leader into a replicated log. Followers confirm each entry. Once a majority confirms, the entry is committed. If the leader dies, the remaining nodes elect a new one. No human intervention needed. Raft is the engine under ECCD, CockroachDB, TiKV, and HashiCorp console. Now, here's where things get ambitious. Google took consensus and built a globally distributed SQL database on top of it. That is Google Spanner, published at OSDI 2012. Spanner gives you SQL, full ACID transactions, and external consistency, meaning every transaction appears to happen at a single instant in real time, even across data centers on different continents. The key innovation is true time. Google puts GPS receivers and atomic clocks in every data center. The TrueTime API exposes a bounded uncertainty interval. You ask, "What time is it?" and TrueTime answers with an interval, earliest and latest possible current time. That uncertainty, called epsilon, is typically just a few milliseconds. Spanner uses that interval as follows. Before revealing a committed transaction, it simply waits out the entire uncertainty window. This commit wait is typically around 7 milliseconds. After waiting, Spanner knows for certain that no other transaction could have a later real-world timestamp assigned an earlier number. Timestamp order equals real-time order. That is external consistency. Spanner runs Google Ads, described in the F1 paper, and is the engine behind Google Cloud Spanner today. Not everyone has GPS receivers and atomic clocks in their data centers, so a generation of new SQL databases applied Spanner's architecture using software clocks instead. CockroachDB, TIDB, and UgiByteDB all give you SQL plus ACID over Raft replicated range-sharded storage. They replace TrueTime with hybrid logical clocks, or HLC. HLC combines a physical wall clock with a logical counter to track causality. It provides strong ordering within a cluster, but without the absolute time-bound TrueTime offers. The practical result? You still get linearizable single-shard transactions and serializable cross-shard transactions. But cross-region commit latency is higher, typically tens of milliseconds rather than Spanner's 7. That is an acceptable trade-off for teams who want global SQL without building a GPS timing infrastructure. At the top of the stack, Raft replicated shards with global SQL, Spanner, CockroachDB, TIDB, give you the full picture. Distributed, sharded, strongly consistent, and still speaking SQL. The cost is commit latency and operational complexity, but that is a far better trade-off than a fragile 2PC coordinator holding the entire system hostage. In the final part, we put all of these pieces together into a reference architecture and walk through real case studies, Discord, Facebook, Instagram, and Google, to see exactly which layer each of them reached for and why. We have covered every major layer: replicas, caches, storage engines, sharding, consistency, and consensus. So now let us see how real companies actually assembled these pieces, and then pull it all into a single reference architecture. Let us start with Discord, because their story spans 6 years and 3 databases and maps directly onto everything we have discussed. In 2017, Discord was storing messages in MySQL, and as the message volume crossed into the billions, MySQL simply could not keep up. They migrated to Cassandra, 177 nodes, consistent hashing, an LSM-Tree storage engine built for write-heavy workloads. For years, that worked well. But by 2023, they were storing trillions of messages, and a new problem had surfaced. Cassandra's JVM garbage collection pauses during compaction were causing P99 read latencies of 40 to 125 milliseconds. A popular Discord server's channel is essentially one hot partition, thousands of users reading the same rows simultaneously. Their fix had 2 parts. First, they built data services in Rust that coalesce concurrent reads for the same key into a single database request. Request coalescing applied at the service layer, not the cache layer. Second, they migrated from Cassandra to ScyllaDB, the C++ re-implementation of the same Cassandra data model, without the JVM and without the GC pauses. The result? 177 Cassandra nodes collapsed down to 72 ScyllaDB nodes, and P99 read latency fell to around 15 milliseconds. That is, consistency model, storage engine choice, and hot partition handling all interacting at once. Now let us look at Facebook's caching layer. As we saw in Part 3, by 2013, Facebook's Memcached deployment was handling over 1 billion cache requests per second, with trillions of items stored across clusters. Two problems emerged at that scale: the thundering herd and stale sets. Facebook solved both with Memcached leases, a token system that lets only the first requester rebuild a value while others wait, and that rejects stale writes if the lease has already been invalidated. For cross-region consistency, McSqueal daemons tail MySQL bin logs and broadcast cache delete messages to every region the moment a write lands. This is what it looks like when caching is no longer a performance nicety. It is load-bearing infrastructure. Instagram's 2012 sharding story is a masterclass in doing a lot with a little. As we saw in Part 5, their 64-bit ID packs 41 bits of millisecond timestamp, 13 bits of shard ID, and 10 bits of per shard sequence. Time-sortable, generated inside a Postgres function, no external service needed. The physical infrastructure was just a handful of Postgres machines, each hosting hundreds of logical shards as separate schemas. Instagram scaled to over 30 million users with roughly 12 engineers. That is the power of a clean sharding design chosen early. Now Vitess, which starts at YouTube and ends at Slack. YouTube's MySQL database was approaching the write throughput limit of a single machine. Rather than rewrite every application query to be shard-aware, they built Vitess as a middleware layer that speaks MySQL protocol, pulls connections, rewrites queries transparently, and handles resharding by splitting ranges automatically. Vitess is now a CNCF graduated project, and Slack adopted it to scale their MySQL fleet horizontally, without rewriting their application. PlanetScale, the database as a service built on Vitess, offers the same sharded MySQL to anyone. This is the pattern. Solve the hard distributed problem once in a middleware layer, and let application teams keep writing plain SQL. The Amazon Dynamo paper from SOSP 2007 deserves its own moment. As we covered in Part 6, it introduced a coherent design vocabulary that an entire generation of NoSQL systems borrowed from. Consistent hashing with virtual nodes, sloppy quorums with hinted handoff, vector clocks for causality, and Merkle trees for anti-entropy. Crucially, it framed SLAs around P99.9 latency targets, 300 milliseconds, not averages, because averages hide the tail. Cassandra, Riak, Voldemort, and the modern DynamoDB service all draw directly from this blueprint. Finally, Google Spanner, which solved the problem everyone thought was unsolvable. Globally distributed, strongly consistent ACID SQL. As we saw in Part 7, the key is true time. GPS receivers and atomic clocks in every Google data center, exposing a bounded clock uncertainty interval, typically under 7 milliseconds. Spanner simply waits out that uncertainty window before revealing a commit, which guarantees that timestamp order equals real-time order. Spanner powers Google Ads, the F1 database, and Cloud Spanner, and it proved that global ACID is achievable if you are willing to engineer the clocks and absorb a few milliseconds of commit latency. Now let us step back and draw the reference architecture that pulls all of this together. At the front sits a load balancer, distributing requests across a pool of stateless application servers. The application servers hit a cache cluster, Redis or Memcached first. Behind the cache sits the sharded primary replica database tier. Multiple primary shards, each with one or more read replicas, accepting writes in parallel. Heavy write workloads emit events onto an async pipeline, Kafka, which feeds downstream consumers, search indexes, analytics warehouses, notification systems. The analytics store sits off the hot path, a columnar system like BigQuery, Redshift, or ClickHouse, optimized for aggregation queries that would be prohibitively expensive on the transactional database. Each layer in this stack was added to solve a specific ceiling. The read replicas are there because the single primary's read throughput was exhausted. The cache is there because the replica's throughput was exhausted, or the latency was too high. The sharding is there because the single primary's write throughput was exhausted. Kafka is there because synchronous fan-out to downstream systems was too slow and too fragile. And the analytics store is there because OLAP queries on the OLTP database were killing transaction latency. Which brings us to the meta lesson of this entire video. Scaling is not about being clever. It is about trading simplicity for capacity, one layer at a time, only when the layer below it is exhausted. A single well-tuned Postgres instance can handle tens of thousands of queries per second, serve millions of users, and run for years with minimal operational burden. The moment you add a read replica, you inherit replication lag and read your own writes anomalies. The moment you add a cache, you inherit cache invalidation complexity. The moment you shard, you lose single machine ACID and cross-shard queries become scattergather. The moment you go eventually consistent, you must reason about convergence windows and conflict resolution. Every technique in this video is a cost, a real, ongoing operational cost that you pay only when the simpler option below it no longer stretches far enough. Discord did not start with ScyllaDB and request coalescing. Instagram did not start with thousands of logical shards. Facebook did not start with leases and McSqueal daemons. They started with the simplest thing that could possibly work, and each layer was earned by exhausting the one below it. That discipline, knowing which problem you actually have before reaching for the next tool, is what separates good systems design from over-engineering. Thanks for watching the full series on database scaling. If any layer in particular sparked questions, the papers and blog posts linked in the description go much deeper. The Dynamo paper, the Spanner paper, the Discord engineering blog, and Kleppmann's designing data-intensive applications are all worth your time.